that the robots can share and can swap. So various pick and place tools like grippers, essentially pneumatic grippers to pick and place parts. The tools are on a tool rack, which is between the two robots, and the robots can share the tool rack. So, and you need to make sure that the two robots don't collide with each other, because that would be a big problem. Would essentially break the robots, the parts, and everything. The project, so this was a European project in collaboration with various universities and companies in Europe. Was about developing plug and produce systems. So plug and produce is a bit like plug and play systems. That's a term that was used in computing a few years ago. So the idea is that you got a dynamic, reconfigurable system with various resources like robots, like there is a shuttle system to move the parts from one resource to another. There are like other devices, sensors, inspection stations to check the quality of the parts that you're making. So the idea was to be able to add or remove production resources from the robotic system dynamically and have the system reconfigure itself to accommodate the new resources, to redistribute the production tasks, because the two robots, each robot can perform different assembly tasks on the same part, or they can perform the same assembly tasks on a different parts. Sorry about it. Don't know if someone is speaking or if it's just some background noise. So in order to offer this, let's say, intelligence, so this is a form of intelligence, so that's why we needed artificial intelligence for this, because manufacturing systems are quite rigid. You can program them, you can tell, you can program the robots, of course. You can say, go here to this point, do this, pick this part, pick it from here, drop it there. But once you program them manually, you run them and without any interruption, and then and that's it. There isn't any sort of update, any dynamic update. So that's why we needed artificial intelligence, to make this more dynamic, to monitor the environment, the available resources, and to update, reconfigure the system automatically. This is another system, another assembly system, completely different, in which we use the same concepts, the same software, the same artificial intelligence. So it's a different robot. It's even smaller, very compact, very fast. It's a Delta robot. It can place very quickly very small parts. This was used by a company in Switzerland to make watches with very, very small parts. This is another assembly system that we used in another project in collaboration with another company in Switzerland. The idea of this project was again about using artificial intelligence to reconfigure, to adapt manufacturing systems. What we did was but here there was, let's say, more data involved. So here there was a form of machine learning where we were capturing data on configurations, changes, mechanical changes made to the machine, changes to, like, for example, pressure of the grippers. So the system was learning which changes were increasing the performance of the system, performance in terms of throughput, cycle time, or quality of the final product. And this information, this knowledge was then used in the future for similar machines or by other operators to do the same sort of configuration on different machines. So it was a form of decision support system. We were not doing reconfiguring systems automatically. We were supporting the user to in configuring systems, because the changes involve mechanical operations that you cannot always do through software. So now, this is some projects, some scenarios, some machines, use cases on manufacturing systems. But manufacturing is also about processes. Processes like additive manufacturing, not just assembly, machining, heat treatments, forging, and other many more processes. Something important something that plays an important role in, let's say, the engineering of the manufacturing processes is simulation, and in particular finite element analysis, which used to, let's say, simulate the processes. So there is a lot of mathematics involved. I don't do finite element analysis, but I contributed to this project to develop a software to support finite element analysis done by engineers by transferring results from different models. So what you do is you model and you simulate a process, let's say some machining process, if you want to analyze the forces, or if you want to study the temperature of a part during some heat treatment process. So you use a model of your part, you do your simulation, you got something like this here. So this part, I can't remember exactly what it was used in aerospace. A lot of this is applied in aerospace. So the different colors represent different level, different stresses, different displacements, distortions, for example, depending on what you are simulating. Now, in manufacturing, you can use different processes in a sequence. You can have what is called a chain in manufacturing processes. You do your simulation on, so for each part, each process of the chain, you do simulation. You use a model of the part. You use a mesh with nodes, elements. That's this sort of mesh structure that you can see here. So you use a different mesh for different processes because different element types, different densities are more suitable depending on what you're simulating. But then when you go from one process, for one stage to the chain to the next, you need to transfer your results across the meshes, because it's not you cannot always use the same type of mesh for different processes. So develop the software to transfer the results from one mesh to another in order to do your finite element analysis, your simulation on the next stage of the chain. It's not necessarily difficult to transfer results. It can be done. It was done already by some colleagues. The challenge was to do this efficiently, because this, let's say, the computation can take a long time, can take hours or even days if you transfer the data sequentially. What I did was to develop a multidimensional data structure to map more efficiently the data from one mesh to another. So given, let's say, an element or a node in one mesh, through an indexing data structure, you can identify very quickly in constant time where to copy your data, in which node or element of the destination mesh to copy your data. There are some interpolations as well involved. There is interpolation techniques which produce different, let's say, with different levels of quality. You can see, depending on the, here the one at the bottom right looks more smooth compared to the one the top left. So different, let's say, quality of results, different errors in interpolation as well. Also different computational performance. But thanks to the indexing data structure, also thanks to some parallel algorithms, this was very efficient. So something that was done originally in hours or days was then carried out in a few seconds. Using both multidimensional indexing data structures and parallel algorithms. Was possible to use, it's not always possible to parallelize your software, depends really on interactions between the different processes. Here, the parallelism was on the data, so it was, let's say, relatively easy to split the mesh across different threads or processes. Now, a particular application of this indexing techniques system, multidimensional data structure, was in additive manufacturing. So additive manufacturing is about 3D printing. They're not entirely sure myself if there is any significant difference, but from a computer science perspective, they are the same thing. So what you do in additive manufacturing is you, let's say, make a part by adding iteratively layers of material. Material could be, in this case, it is metal, but could be also something else. So here the part that we made is manifold, was used in aerospace, in airplanes essentially, but not sure exactly where. I'm not always fully aware of the actual application of the this processes or the parts that were made. Now, a problem with additive manufacturing is that the part, well, it is a problem in general of manufacturing. The part that you make is not perfect. You got your perfect design, you got your CAD model with all the dimensions, all the tolerances. But then when you make the part through additive manufacturing, through machining or other manufacturing processes, the part is not perfect. There are imperfections. The shape may not be right, the dimensions may not be exactly what you expected. This is a problem in particular in additive manufacturing because the technologies are relatively new, so some technology is not mature enough. So what happens is that there can be distortions. So your part is distorted in some points. Maybe the distortions are not visible, but if you measure then the part, in this case, if you scan the part with a laser, and you compare the part that you made with your design and with your CAD model that you used to create the part, then you can find some, you can identify distortions. So in this case, the distortions, well, actually, we can see here, depending on the colors, so can go, there were distortions of plus minus 400 micron, which you may or may not be able to see with your eyes, but if you inspect the part, you can measure this and notice these distortions. If that's, let's say, now the distortions, could be a problem, but not necessarily. It depends really on your requirements. So usually you got a tolerance that you evaluate to see if the part is good or bad. If it is intolerance, it is good. If it is out of tolerance, you don't accept it. You do some rework, and you scrap the part, and you make a new part. The idea of the project was to compensate for the distortions. You could minimize the distortions. There is a lot of research at the moment to minimize the distortions, but another approach is to make your part, measure the distortions, and then create a new model that compensates for the distortions. And then you use that model to make a new part, which is what we did. So this is the part that was made, the distortions that were measured. Then we created a new model compensating the distortions. So it was a new model that was not perfect, but then when actually made with the additive manufacturing machine, was producing a part that was closer to what we expected, what we wanted. And this is the part that was made with the new model, and it is mostly green. So the distortions were reduced from 400 micron to approximately 100 micron. Again, it was not perfect, but the difference is significant. So maybe depending on your requirements, your tolerances, maybe you were not happy with 400 micron, and now you're happy with 100 micron, or maybe that's still not enough. Maybe you need to reduce even more your distortions. Another project which was about machining. So machining is about cutting material. So it is, let's say, in a way, the opposite of additive manufacturing. In machining, you got like a block of metal, and you got some cutting tools to cut the material to make it the shape that you want, to make your part. The problem with machining is that there are vibrations in your cutting tool. That's something called chatter. Vibrations are not good because they cause your part, the surface that you cut, not to be smooth enough. So you will have some roughness, some imperfections, and also that's not good for your tool, because if it vibrates, then it can wear more quickly. So the objective was to reduce chatter, and this is an old problem, it's not a new problem. There are many mathematical models, physics-based models to reduce chatter in machining. They work, they're not perfect, but they work as far as I know. Now, we worked on a completely different approach. Well, maybe not exactly completely different, but because we still used some physics-based models, but we also used data, and we created a digital twin, which is, let's say, a representation of your physical environment in a software, in your virtual environment. And you use your digital twin to not only to model your physical environment, but to monitor what's happening in your physical environment and update your physical environment. So there is continuous communication between the physical environment, the machine in this case, and the software, your digital twin. So the digital twin receives, in this case, receives data on the process, on the forces. We were measuring the forces that were applied in order to sort of measure estimate the chatter, the vibrations, and compensate for that, changes parameters like the speed of the cutting tool or the depth of the cutting tool in order to reduce the chatter. So this was a dynamic process. It was not what you usually do, that you got your mathematical model to determine all the values of your parameters, and then you use those parameters, speed, cutting depth, and that's it. If your part is good, then it's good. If it's not good, then you scrap it, and or you change the process, the parameters for a new part. So this is very much more dynamic, and with a continuous update thanks to the digital twin. So this is again another form of intelligence. So the digital twin is a form of artificial intelligence that is not. It offers also some level of autonomy, because less involvement from the human, because it's not you changing the parameters, the cutting parameters. It is the digital twin. So something that we already said a few times is that the parts that you make with your manufacturing processes, your manufacturing systems may not be perfect. How do you know if they are perfect or good enough? They're never perfect, and that you don't need necessarily something perfect. But the question is if they are within or out of tolerance. To evaluate your tolerances, you measure the parts. That's what you do with the dimensional methodology. And what you do is you inspect the various features, 3D features like cylinders, for example, you got an engine here, or planes or curves. You want to be sure that a cylinder, for example, is actually a cylinder, not a different shape, or that it measure like the things like length of depth of a cylinder, or the meter of a cylinder, or length of a curve, or other geometrical features. Also, position orientation of maybe you got the right feature, but it's not in the right orientation. So you can do quite a lot with by measuring. You can measure a lot of different aspects, characteristics. There are systems, there are machines. Here you can see a touch trigger probe. It is essentially something with a tip, a very small tip, that takes touches on the part, beep, beep, beep. And for example, if you got like a circle, you need to take 3 touches, and then you do some interpolation to fit a circle with the 3 points. Because you need at least 3 points. You cannot fit a circle with 2 points. So you take a certain number of touches in order to then fit your features with those touches, and compare the features that you measured against the features in your model to see if they are within or out of tolerance. You can also use a laser, which is much faster, that doesn't doesn't make contact with the part. It's not necessarily very accurate. It also is not able to go deep into some features. If you got like a hole, very deep hole with the laser, you cannot inspect, the hole inside. So now these probes, the laser or touch trigger probe, are attached to a machine called CMM, Coordinated Measuring Machine. So I worked quite a lot in industry with CMMs. You don't build the machines again, because I don't work on the mechanical, problems, but I worked on the software. So the software that I developed is this one. It is called CAMI, Computer-Aided Manufacturing Inspection Output. So this is one of the most popular metrology software. There are others, so I'm not going to, well, I don't work for this company anymore, but I mentioned also some competitors as well. So what do you do with this software? You got your CAD model of the part that you want to inspect, and you create a program to inspect the part. In your program, you say, I want to use this probe, I want to use this angle for the probe, I want to inspect these features in this order, I want to take this number of touches, I want to move from one feature to another this way. So you need to specify the path of your coordinated measuring machine, where to go from one feature to another. So you write this program, and you do this manually. We will discuss then the implications later. And then what you get, so you can simulate this on your computer. The program that you write can be simulated. So that's offline programming and simulation. And then you run this on the CMM, on the actual part with the real machine. And you get an inspection report that tells you all the features that are in or out of tolerance. So you can see all the nominal values, the actual values, the error, and the deviations from the tolerance. Now, this is pretty much standard. Software like this has been around for quite some time. There is not much innovation nowadays. There should be, and we'll see in which way, what sort of innovation we will need. But it's, and there is something similar as well for making the parts. So if you got like a CNC machine to cut materials, you do something similar. You write your program to control the machine to say, go here, go there, cut material here, cut material there. This is, let's say, the two things are sort of symmetric. When you inspect, you measure the part that you already made. When you machine, you got a program to say the various features that you want to make by cutting material. And probably it's the same with additive manufacture. Although I'm not used to the software, but I guess, well, in that case, it is actually probably easier because you create your model and then you simply send your model to the machine. And there isn't really any path, or maybe there is some path that you use to create the various layers, but that's I'm not sure you actually program that. I don't know. I don't know how that works. So now, what is missing in the metrology software? So this is something that I started to work in the past, and I think there is quite a lot still going on. So this is also about the role of artificial intelligence in metrology. So you can clearly, write programs to inspect the parts. Now, one problem is to monitor the performance of your machine. Now, what is the problem with performance? So first of all, if you got, let's say, many machines, many CMMs, you want to, there is a similar problem with other machines. This is a general problem, not just about metrology. If you got multiple machines, you want to maximize the utilization. You don't want, machines to spend a lot of time without doing nothing, idle time. You want to, make the best use of them. So you want to maximize utilization, and also you want to know when to do maintenance. Maintenance for SMM involves, for example, recalibrate your probes, which is something that you do periodically, or you do when something happens. If, for example, you got like, if you, let's say, you crash your probe into the part, or if you bend the tip of the probe slightly, then your measurements are not reliable anymore. So you need to, you can still, if the tip of the probe is bent, you can still use it, but you need to recalibrate your probe to compensate for the bent tip. But you need to recalibrate, otherwise your measurements will not mean anything, will not be reliable. So the problem is that you need to know when this happens, when you bend the tip. And so either you are there by the machine and you watch what is happening, or you need to sort of have some intelligent monitoring, estimate, looking at monitor the trends in the quality of your parts. So here we are, for example, looking at the diameter of circles or and we see that at some point the values drop. So there is a significant difference in the diameter of the circles that we are measuring. Could be that the parts are not good, but could also be that there is an issue in the machine. It's difficult to guess, so maybe you need more data. But clearly you can, monitor your process and identify patterns. deviations from the, let's say, from your trends. And you can do this using machine learning, which is important part of artificial intelligence. So this is a real-time fault detection. It allows you to realize when you need to do some maintenance or when there is a fault that you need to fix. So now, so the title of the presentation was Synthesis of Manufacturing Process Plans. So we spoke, but we're actually covering not just planning, we're covering monitoring, we're covering quite a lot of things. But now, focusing on planning, by process, so first of all, by process planning, we mean a lot of things. Planning is about identifying the resources, the equipment that you need to manufacture your parts, identify the best manufacturing processes, the best inspection strategies. So it's about identify the appropriate resources, how to use those resources, and how to allocate your various production tasks to the resources that you got available. One particular problem is process planning is path planning. So this is now for CMMs, but there is a similar problem for other manufacturing processes like machining, or for robots. Robots work in an environment where they have to move, so you want to plan, the moves of the robots. This is a general problem. There are solutions, but there isn't a general solution. And even if we focus on CMMs, the problem is not solved because there isn't a general solution. There is software, there is some artificial intelligence that can help you to solve specific problems, but for problems related to specific objectives that you want to achieve. But what if you got multiple objectives? So what are the objectives that I'm talking about? So for example, you want to avoid collisions. If you move your probe from one feature to another, you don't want to go through the part. You need to go around, find a path that doesn't crash your probe in the part or in something else around the part. You want to minimize the time, the distance as well, in order to minimize the cost as well. To minimize the energy consumption, that's another objective. So collisions, we mentioned collisions. But then for CMMs, there are specific objectives. So you want to also to identify the best probe for each feature and the best probe angle, because you can swap probes that are different. You can use a laser for certain features. You can use a touch trigger probe for other features. You can use a scanning probe, which is a probe that keeps touch with the part, as opposed to keeping separate individual touches. You may also want to minimize the number of tool changes, because that also has an effect on the time, on the inspection time, on the cost, energy consumption, also wear of the tools. So different objectives. It's difficult to optimize all these objectives. So path planning for CMMs is still a big issue. Again, there are solutions, but solutions are for specific problems. There isn't a general solution that helps you to solve all your problems at the same time. This is one particular type of CMM. There are two arms. So this is it's not a vertical CMM. So something I did not say here actually. I don't know if you realized. So the way CMM works is that it goes along three directions: X, Y, and Z. Okay. So you got that spindle there that goes up and down, backwards, forwards, left and right. And then the probe can rotate. There are two, what are they called? Two axes. So in total, there are 5 axes, 3 axes X, Y, and Z for the CMM, and 2 axes for the probe. So that's a classical CMM. This is another CMM with the 2 arms, horizontal. The problem here is which arm is doing what, which program is running on each arm, which features you are inspecting on using each arm. Now, this is a typical application is to inspect the body of a car. And in that case, actually, the control and the path planning are, let's say, are not a big problem because the car is symmetric. So each arm, so you got an arm on the left and on the right, and they run the same program. They run a symmetric program. Not exactly the same. It is like a reflected program with the opposite angles for the 2 sides of the part of the car in this case. So path planning is a type of process planning. Program generation is, let's say, a more general version of path planning. What is automatic program generation? You go to your design or the part that you want to either make or inspect, and then from that, you go to the engineer, creating the program to run on the CMM if you want to inspect the part, or to run on another machine, a CNC machine, if you want to make the part. This programming stage is manual. You cannot automatically create the program from the design of your part. The software can help you to create, for example, can help you with path planning to some extent, but path planning is only a part of the full picture, because still you have to select the probes, the angles, the features, what you want to inspect in the features, you want to evaluate the tolerances. So there is much more information apart from the simple paths. All this cannot be easily automated. So there isn't a software that from the design can create your inspection program. There is software that can support you in doing this, but there is still a lot of human involvement of the engineers. So this is not a problem. And then assuming that you can actually generate automatically the program, then there is a fundamental question: how can you prove that the program is correct? And in order to do that, you need to look at the semantics of your design and the semantics of your program, and compare the two, check that the two are equivalent.
Excuse me to interrupt.
Yeah.
Actually, there is information for participants. So we have given a feedback link in the chat. We request all the participants to fill the feedback link. And the last 10 minutes is for the question session. So is it possible to finish in 5 minutes?
Yes, absolutely.
Okay. So just a reminder for all the participants, kindly check the chat box. We have given the feedback link in there. Thank you.
Yeah, okay, I can see now the chat. Yeah, I can see now some comments. Okay. Yeah, I was just focusing on the presentation. I was not looking at what else is happening. Okay, I'll finish in 5 minutes. Yeah, got a few more slides. Now going back, so this is the machine, the assembly system that I was showing you in the first slides, with the 2 robots and the shuttle system to move the parts around. So something we did not say, which is not very relevant to my research really, is the product that we were making. So the product was really a sample product that was nothing sophisticated. So it was a hinge. Here you can see various parts. There are 2 lifts. There is a detent tube that you put inside. There are some bolts and springs. There is a process assembly process where you say, put these two parts together, put the two leaves together, then put the tube inside, put the balls inside. The question is, if you then you want to, let's say, control this with software, you need to represent this in your software. You need a sort of language to represent this. And a simple representation involves the use of something called the label transition system, which is a form of state machine, finite state automata. So you can represent the recipe, which is the instructions to make your product. And you can do something similar to represent your resources, to specify what the robots can do, what operations the robots can do. So now here, so this is a different example. It's not related to the operations to make this hinge. So we've got operations like insert, separate, engrave, apply glue, and get force to inspect like the force. So you can present the capabilities of your resources with this sort of language representation. And then the question, which is something I'm working on at the moment, is how to orchestrate, how to coordinate your resources to make your product. So you can do that manually, but if you want to synthesize a process plan to automate this process, you need to implement this in a software. And one approach is to combine the various label transition systems to look at all the possible states of each resource and see the various transitions where you can go from in each resource, from which state to which state you can go. And that's what you get. So here, so now if you combine all these diagrams, you get something very big, something huge, because you got a combinatorial explosion of this state space or the search space or your search space. And within this search space, you need to identify the path that takes you from to your final product, that allows you to perform, to allocate all the assembly tasks to the various resources and get at the end your final product. This is your process plan, and the algorithms for doing this are your synthesis algorithms, the algorithms to synthesize, to generate automatically your process plan. And this is an example of a process plan. This is which sort of, so the diagram here on the left specifies the various states, transitions of the various resources to go from your initial state, which is where all the resources are in S0 state, to the final state where you reached basically the end here, the state F of your process recipe with the final product that you wanted to assemble. So now this maybe looks complicated, I don't know, but can be automated. We developed a software for doing this, and we actually got two tools for doing this. One uses label transition systems, and the other one uses even more complicated, more sophisticated, more powerful language, which is